induction. Going to start off with an inequality one. There was a rumour around that you couldn't have an inequality induction in 3-unit. As you saw yesterday, there was one. You are more likely to see an inequality one in an extension 2 one, but you can get them in 3-unit, I guess is what I'm trying to say. Alright, let's start off. Test. N equals 1. Left hand side is 1. Right hand side is 1. Yes, it is true to say it's less than or equal to. Remember what you're saying, less than or equal to. Well, it's equal to, so yes, it is less than or equal to. Now, I'm not going to write the whole bit out. No, before anyone asks. The answer is no. Okay? You cannot write yours out like this. I'm just saving a little bit of time here. So, that would be our assumption. That'll be what we're trying to prove. So, it is a series type. So, I'll set it up like a series type. Sum to k plus the k plus 1th term. That way we can get our assumption in. And we know our assumption, so up to the 1 on k squared was less than or equal to 2 minus 1 on k. We want to make that right hand side less than or equal to, what was it? 2 minus, just 1 on k plus 1, was it? Yeah. Okay. Well, I'm not going to touch the 2. So I've already got the 2 there, so I'm stupid to put that into the fraction. I don't need to bring it out again. So I want to play with a fraction. So that line would be equal to, if I turn that all into one fraction, so ideally what I'd like here, the common denominator is k plus 1 squared. So I would like the numerator to be k plus 1. Then I could cancel and I've got the 1 on k plus 1. Unfortunately the top doesn't work out to be that. The top is k squared plus k plus 1. So what did I say I wanted? k plus 1. So that is what I would like. K plus 1, in other words, k squared plus k. Unfortunately, I've got this other minus 1 on k hanging around. But remember, I'm dealing with an inequality rather than an equation. So I can say that this second last line is less than the last line. Because I'm always minusing something from it. And I know k is positive, so I've always got to be subtracting a positive number. And now I'm left with what I want. The k plus 1 will cancel, getting me the 1 on k plus 1 that I wanted. And so then if we read down, I can now say, well, the left-hand side is less than or equal to the last line. And hence, etc., 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 etc. The other ones that are a bit different in extension 2, these ones where you have recursion formulas for the series. So rather than writing the series as a general term, you have this recursive one where they say, oh well, the first term's this, and then to create every subsequent term, you do this. So our series, or sequence in this case, the first term is the square root of 2, and then to create every term after that, we find the square root of 2 plus the previous term. So we're going to show that every single term in this sequence is always less than 2. So test for 1. Well, they told us the first term is the square root of 2, and square root of 2 is, of course, less than 2. So I'm going to assume that the kth term is less than 2. I want to prove the k plus 1th term is less than 2. Now, I can use my recurrence formula. Remember, this is not what we're trying to prove. This is given to us. That's a fact. So I can use that. So I can say ak plus 1 is the square root of 2 plus ak. My assumption is that term k is less than 2. If I sub that in, I can now say, oh, well, this has got to be less than the square root of 2 plus 2. Well, 2 plus 2 is 4. And square root of 4 is 2. So ak plus 1 will be 2. Or less than 2, sorry, because of the less than sign there, if you read down. So there it is. Actually comes out quite nicely. Sometimes you might be playing with more than one sequence. And in this case, the sequences are sort of linked. So we're saying the first term in the x sequence is 5. First term in the y sequence is 2. To get the next term, I get the nth term out of both sequences and average them. to get the y1, I get the x and the y term from the previous one, multiply them together, multiply by 2, well you can see, and divide by x plus y. We have to prove that every time we multiply xn with yn, we'll get 10 every single time. So, well, we can see x1 and y1, 5 times 2 is 10, so fair enough. When we do it for n equals 1, it works. Looks horrible, but actually, it's quite nice. Because we're going to assume xk, yk is 10. I want to prove xk plus 1, yk plus 1 is 10. So I'll sub in the formulae, and look what happens. xk plus yk cancels, 2 cancels, I'm left with xk, yk, which was my assumption, and I've assumed that to be 10. Bingo, out it comes. So sometimes they can look terrible, but actually they come out really quick. Fibonacci sequence, personal favourite. I always like the Fibonacci's. Now, if you remember the Fibonacci sequence, the classic one starts with 1, and then it goes 1, 1, and then you add the 2 previous terms to get the next term. So it goes 1, 1, 2, 3, 5, 8, 13, 21. What we're going to prove is that every term is less than this wonderful number in here, which I hope you're recognising, to the power of, it's phi. It's the irrational number. What's phi? What's phi? 1 plus root 5 on 2, thanks for asking. It's the golden ratio. Let's do the proof. But in this case, remember, I'm going to use this linking equation, but I'm going to have to substitute in both the nth term and the nth minus 1 term, which means I'm going to have to make 2 assumptions. Because I'm going to have to assume both my expression for an and an minus 1 is correct. So if I'm making 2 assumptions, then I need to test for n equals 1 and 2. Because if you think about when you go to your last step, what are you going to say? You're going to say, oh, hence I've proved it's true for n plus 1 if it's true for n and n minus 1. So you're going to say that. So then you're going to say, oh, well, since I've proved it true for 1 and 2, therefore it's true for 3. And now I know it's true for 2 and 3, it's true for 4, and so on, and so on. So I'm going to need to do 2 assumptions here. So A1 is 1, and yes indeed, it is less than 1.62. A2, well, that be the golden ratio squared. That turns out to be 2.62. So we're good for 1 and 2. So I'm going to assume both AK minus 1 and AK are correct. Now I'm going to prove true for n equals k plus 1. So that's what we're trying to prove. There's my linking equation. Let's substitute in our assumptions. We're trying to make this 1 plus root 5 on 2 to the power of k plus 1. Okay. Well, fortunately, there's already a common factor there. I think, did I do that first? Yeah. I pulled out the common factor, but notice I did something different. Normally when we pull out the common factor, we pull out the lowest power, but I didn't. This time I pulled out the power that I want, because I want to end up with the power of k plus 1. So now all I really have to do is play with these brackets and show it's less than 1, or equal to. So let's have a look inside the brackets. Alright, so, well, power minus 1 just means reciprocal. Power minus 2, reciprocal squared. So in the second one, that's 1 plus root 5 squared on the bottom. That means I've got 2 lots of 1 plus root 5 plus 4 on the top, giving me 6 plus 2 root 5. And I can see people getting excited even as I speak, because you've recognised that, hang on, 6 plus 2 root 5 is 1 plus root 5 squared. And so they cancel, and I'm left with power of k plus 1. So reading down, I can now say, oh yes, ak plus 1 is less than the last line. In the handouts, I put in a sheet there with some mixed induction questions.